also known as EVT. Before we get into what the extreme value theorem is, I do want to talk about one last thing about the relationship between f prime and f double prime. As part of your homework tonight, I've actually assigned some problems where I've given you graphs, and you have to identify which function is the function, which function is the derivative, which function is the second derivative. So relationships between f prime, and f double prime. Let's first talk about a function, y equals f of x. So if I gave you a function y equals f of x, and the graph looked like this, all right, as I can see from here, and I'm gonna end up overlapping these ones. The main properties, first off, the main properties I can see are the extremes, the end behaviors. So I can see that this function is increasing at the far right and therefore decreasing on the far left in this example. One of the first relationships is that the derivative will always have same end behavior to the right. And mostly we're focusing on polynomials on these problems. Excuse me. And it will be opposite on the left. Now this comes from because the function is increasing to the right, that means its derivative must be positive. So as such, the function is pointing up, so, and this is going to be y equals f prime of x. Therefore, its derivative must also point up as well. Now, if we notice, if we're reading this left to right, it looks like it's decreasing left to right. But remember, we read right to left. So even though the function itself is decreasing, we say that the function, reading from left to right, is actually still increasing. So it's going to be the opposite. So its derivative, since it points down over here, will actually point up over there. So one of the main ways to tell if one is a function and derivative will be, and when you're doing your homework, is that the left-hand side will have to point opposite. Now, this should be able to give you one of the answers, all right? Because basically, one of them will have two of them pointing up, or two of them pointing in the same direction to the left-hand side, and one of them pointing in the opposite direction. So you know the ones that are pointing in the same direction to the left are not the function in its derivative. It'd be the function in its second derivative. So if what I'm trying to say is that if you have two graphs that are both pointing up, one of these functions has to be f, and one of these functions has to be f prime. Now, which one is which? You have to figure out that part. But one of them would be the function, and one of them would be the derivative if they're both pointing in the same direction in the left-hand side. So that's it's a trick, it's a property that we know. Now, because this is a function, we always want to look at extrema. So if we notice, this graph has a relative extrema here and a relative extrema here. So it should always be noted that relative extremas are zeros for the derivative. So if that's a relative extrema, then that has to be a 0 for this graph, and this has to be a 0 for this graph. So I know that this graph is going to go here and then it's going to come back up to here. Now, I should also note that if I have a point of inflection, that's going to respond to a minimum for that one. Now, that one's not as much of a biggie right there, but a point of inflection should match up to a relative extrema for its derivative. Talking about y equals f double prime of x. Well, f double prime of x, since this is pointing up, we got to look at the red because it's its derivative. This one will also point up to the right. So all three have to point in the same direction on the right-hand side. This is the derivative of red, so that means it has to point down on the left-hand side. The function and its second derivative will point in the same direction. The one function, and so this one's, it's a nice trick here, basically is the following. The function that's not pointing in the same direction as the other two on the left-hand side is the derivative. It's the one that's in the middle. So f prime will always be pointing to on its own in a different direction on the left-hand side. It's a nice trick to be able to identify this common AP exam question. Now, I notice that there's a relative extrema right here. So when there's that point of inflection, the second derivative, that means that this has to be over here. Now, this typically should have been a line, but we had just right here. So it only crosses the x-axis at 1. Now, we can also talk about the degrees and turning points. For polynomials, and this is a very big kicker here. For polynomials, degrees decrease by 1 for each derivative. And the same thing happens for the turning points. For polynomials, turning points decrease by 1 for each derivative. Now, these are some tricks for polynomials, all right? So when you're dealing with a polynomial, you can look at those end behaviors. And that's usually how you can even almost get to the answer. And then you can see like, oh, well, this one has like degree 3, this one has degree 1. Oh, the degree 1 has to be the second derivative because you can't, its derivative would be a line. Sometimes you're dealing with functions that are not polynomials. And when you're dealing with non-polynomial functions, then you really have to look at this idea of where there's an extrema, its derivative better be a 0. So you want to look at the relationship between extremas and zeros are the big keys. So if a function has an extrema, every single place a function has an extrema, its derivative should have a 0. If a function has an extrema, its derivative should have a 0. And that's just that's the one you'll have a problem on your homework on Delta Math that is asking you that type of problems, that part. Okay. All right, let's get into the main part of our actual lesson here. And that is the extreme value theorem. EVT. These are what is known. This is one of 3 existence theorems. Next week on Monday, I'm going to show you Monday and Tuesday. I'm going to show you the other 2 existence theorems. All right. So they're called existence theorems. This must exist, basically. There must be at least once there must be something that exists, is the idea. Now, there's a condition / requirement and that requirement is that f of x must be continuous on the closed interval a to b. So for EVT, to apply, the function must be continuous. So sometimes they'll say, there'll be multiple choice questions on the AP exam where the function isn't continuous, and they'll say like, why doesn't EVT work, or why doesn't the extreme value theorem occur, or why is there not why talking about why it doesn't work, and we're like, well, because it's not continuous. What does EVT state? Well, EVT states that if f of x is continuous on the interval a to b, then there must exist a point f of c that is greater than or equal to all the points f of x on the interval on a to b. Now, a lot of people do not understand what this part means right here. All this says right here is absolute max. Now, I write it this way because on the AP exam, they will note this. This is a very common one. They'll show this one right here. It just says there's a point that's higher. There's an output that's bigger. That's the biggest output. All right. So there is a point that is bigger than all of the other points. Actually, I think I messed this part right here up. I'm gonna add that sorry. And a point f of c that is less than or equal to, f of k that is less than or equal to f of x for c. Oh, I missed this part of it. Sorry, for a less than or equal to c less than or equal to b. And this one right here is for a less than or equal to k less than or equal to b. And once again, this part right here is just referring to an absolute minimum. Now, in your tonight's homework, you do not have to prove this. In tonight's homework, there is a point. You just have to do the properties. I'm going to go into it a little bit more tomorrow about why it actually works. So I will go into tomorrow a little bit more about why EVT is true. Basically, in layman's terms, simply put, there must be oh, sorry, I'm missing one last line. Why am I missing so many things? At the endpoints or critical points. Let me add that last part, and I'm sorry for missing that line. So it must occur at the endpoints or the critical points. All right? It can only happen there. It can only happen at the critical points. And the critical points, which I haven't really talked about too much, or I need to elaborate a little bit. When we say critical points, this is when the derivative is equal to 0 or the derivative is undefined. Now, in your homework, you're not going to be working with undefined ones right now. That's the trickier of the assignment, is these undefineds. I don't want to put too much focus on it. I want to cover, because I do want to cover everything on the exam. But it's one of those things where it doesn't, the undefineds really don't happen as frequently as we will care to spend the time and energy that we have within the course. But when the derivative is undefined, this can also happen because this indicates a sharp turn. So when there's, and that's what I'm going to talk about tomorrow, the idea of when f prime equals 0, we have a horizontal tangent, which is a potential relative maximum or relative minimum. And when f prime of x is undefined, we have a sharp turn, which could also indicate a relative minimum or relative maximum. Simply put, there must be a max and a min, and they can only occur at x equals a, x equals b, or x equals c for the critical points. So some of us sometimes refer to this as the candidates test. As such, we find the critical points, the critical point x values, and then compare outputs to endpoints. When I say the word max, please note that I always mean absolute max, but we will just say the word max, and the same thing with min. So when I say the max or the min, I really mean the absolute max or the min is largest and smallest outputs. Sounds a lot more complicated than it actually is. So there is some calculus and theories, and if we had more time, I would go, and tomorrow I'm going to try to spend a little bit of time into it, of going into why the existence theorem, the extreme value theorem works. Now, the wording that we use in calculus, it looks a little bit weird at times, but basically it's just saying there's a maximum and there has to be a minimum. And and more importantly, they can only occur at the endpoints or the critical points. Let me show you a graph. Here's a graph. Like here. So this is the graph of y equals f of x on the interval a to b. Now, if we notice this graph in this case has 1, 2, 3, 4 critical points, we say. One critical point here, we'll call that critical point 1. A critical point here, we'll call that critical point 2. A critical point here, we'll call that critical point 3. And a critical point here, we'll call that critical point 4. So this graph has 4 critical points where the derivative is 0 in each of these places. Now, you're going to do these analytically. So you're going to find a derivative and you're going to set the derivative equal to 0 to find these values. But visually, this is what happens. And then we have the values as well. So what the extreme value theorem says is that the max and the min can only occur at f of a, f of c1, f of c2, f of c3, f of c4, or f of b. The max, and the min has to be one of these values. And when we say these values, we're talking about the output. Must be one of these outputs. It cannot be any other ones. And that's what the EVT tells us. That's the nice thing about EVT. Like, we don't have to check anything, and our justification becomes very easy, because if we just identify all the potential candidates, we can refer to this as the candidates test as well. You might see that in some textbooks. It says that, hey, if you find all the critical points and you plug them into the function, not the derivative, but the function, and you see which one gives it, you'll find the Vmax or the Vmin. Now, which value is going to give me the biggest number in this instance? Which of these outputs will be the biggest value? Look at the graph. Based on this graph, which one's going to be the biggest one? Based on this graph, which one is the biggest value? A, f of A, f of C1, f of C2, f of C3, f of C4, or f of B? Not, it's not, this is a algebra 1, pre-algebra type question. Which of those values is the biggest value? Looking at that graph, which one is going to be the biggest value? A, f of A. So this right here is the absolute maximum right here. And the absolute minimum would be occurs at C3. So this value would become the absolute minimum. Now, I do want to point out that these are still relative extremas. All of them are really relative extremas. We don't really talk about relative extremas at the endpoints, but they're still relative extrema. This value here is a relative maximum. This is a relative maximum. And this is a relative maximum. All right, so you have three relative maximums if we think about this graph. One that has here, one that has here, one that has here. So this graph on the closed interval, counting the endpoints, has three relative maximums. But only one relative maximum can be the maximum. And that one is this one over here. And it occurs at the endpoint. This graph has two relative minimums. Oh, sorry, three relative minimums. But only one of those three relative minimums can be the absolute minimum. And that is this one right here. So this graph has three relative maximums and three relative minimums on the closed interval. Of those relative maximum, one of them is the biggest. Of the relative minimums, one of them is the smallest. Now, you might utilize your calculator to find the values. I mean, you're going to input them. So let's look at a quick example. Now, this is really helpful when you're doing things like, remember when you did those, like, here's a quadratic, or you had a function, you had to find the biggest value. You might have had it in a project, and you had to use a calculator, and you had to use some different features. And now we can just use calculus. So here's an example. The function f of x is x cubed plus 2x squared minus 5, and we're going to go from the closed interval -3 to 4. Is this function continuous? Yes or no? On the interval -3 to 4. Yes, thank you. This is continuous for actually all real numbers because it's a polynomial. So therefore, it is continuous from -3 to 4. This is sometimes a trick problem. You know, when we're dealing with polynomials, you're fine. But sometimes they give you a function on the AP exam. They'll give you a function that's not continuous, and then the answers will be like 3, -6, 0, and not continuous. And you do all this work, and you realize, oh, the answer was just the function was not continuous, so there was none. You know, you couldn't do that. So the process here is the process that we do for like finding relative minimums. So the first part is to find, step 1, find the critical points. All right. And how do we find critical points? Now this is where the work becomes very redundant. Oh, I never even stated the question. Find all absolute extrema. Justify. Sorry, I didn't even give the instruction. We're just finding all the absolute extremas. It might say find the absolute max, or it might just say find the max, find the min, find the max and min, justify. So first step, find the critical points. How do I find critical points, everybody? Come on, somebody. It's like the most common thing we do in calculus. You know, some of you, yeah, first thing is find the derivative, but more importantly, we're going to find the derivative and we're going to set it equal to 0. Okay, so it's critical points, set the derivative equal to 0. This gives me 3x squared plus 4x equals 0. How do I solve this? Oh, come on, class.
Do you do x parentheses?
Yeah, we factor out an x. So x, 3x plus 4 equal to 0. This gives me x equals 0 and x equals -4/3. Now, disclaimer. Only use the critical points within the closed interval. They're both inside the closed interval, but sometimes you get one that's outside the interval. So for example, if I got an answer that was like x equals 6, I would not use it because I'm looking only for the absolute extrema within this interval. All right. Now, step 2. I call it candidate's test for really simple. But what I mean by the candidate's test is that we just plug in endpoint and critical point x values to the function finding extrema. So I don't want to say the function f of x. It's the function that, you might say, original function, something you likely like to say. But in this case, we're trying to find the maximum. We're trying to find the extrema for f of x. We're trying to find the extrema for f of x. So we're going to plug back into f of x. So I need to find 4 values. I need to find f of -3. I like to put them in order. And I'm also going to have to find f of 4. All right. Some people like to put the f of -3 and f of 4 right next to each other. I like to do this just to make sure that both my critical points, all the critical points that I find, are inside. It doesn't matter. There's no order. I also need to find f of 0 and f of -4/3. I just plug them back in. Now you might use a calculator to do this. We're just plugging them into this function up here, x cubed plus 2x squared minus 5. I don't care how you get that value, as long as you can get that value. Like, for example, f of 0 is the easiest one. What is f of 0? We can do that in our head. What is f of 0? We can do that in our head. Thank you. -5. F of 0 is -5, right? It's just 0 cubed plus 2 times 0 squared minus 5. 0 cubed plus 2 times 0 squared minus 5. But we can do that in our head. It's -5 for that. F of -3, -3 cubed plus 2 times -3 squared minus 5. You can just you don't have to, you're just plugging them in. Now, if you do this in your calculator, we get -14. F of -4/3 gives me -4/3 parentheses cubed plus 2 times -4/3 squared minus 5. And in your homework, I don't think you get any decimal or fraction numbers. I think they're all nice values. This gives me an -3.8148. I know it's a weird number. It doesn't really matter how many decimal places we go to. We just need to make sure that we reference it. I mean, it should be 3 decimal places. And f of 4 would be 4 cubed plus 2 times 4 squared minus 5, which would give me 91. All right, so what is the relative maximum? What is the maximum? Not where. What is the relative maximum? Okay, f of 4. So this is the max. And what is the relative minimum? Yeah, f of -3. So this is the minimum. And here's the beautiful thing. This is a justification. So you don't have to write any words to justify. That's a justification. By showing that work, and when I say showing the work, you really, I'm just referring to these. You don't really need that work within the middle. You just give me the values. If you've checked all possible candidates, that's justification. So there is and I like to just do them all together. We have a relative minimum of -14 at x equals -3. You might say -3 comma -14. Sometimes they ask you for the point. Typically, this is how I like to write my answer. Sometimes you might see it as at -3 comma -14. You might see that. And we have a relative max of 91 at x equals 4. Once again, you might see it as a coordinate 4 comma 91. Boom. Want to see another example? I need a straightforward example? Yes or no? Are we good? Okay, yes. Let's do an easy one. F of x equals, can someone give me a quadratic? Give me a quadratic function. Any quadratic function. Somebody, you want an example?
Wait, do you want the whole thing?
Just give me a quadratic function. That's not a quadratic, Mana. Thank you. I got x squared minus 10x plus 25. Okay. Any quadratic was good. Now, we know from our advanced algebra studies, we also know from our pre-calculus studies that this graph is concave up always. This graph looks like this. Therefore, it's going to have a relative minimum, most likely, right? I'm going to look on the interval. We're going to go on the interval 0 to 6. Okay, so my interval is 0 to 6. Now, I know the relative minimum, the absolute minimum, is going to occur at the vertex if the vertex is inside. I know that, but we're going to go through the process anyways. And once again, we're going to find the absolute extrema on the given interval, and we want to justify. And justify and just plugging them in. It's kind of part of the process. All right, we find a derivative. What's my derivative? F prime of x is?
2x minus 10.
And I'm going to do what?
What's this do?
Good, that gives me x equals?
Positive 5.
+5. +5 is inside the interval. Good. What do I do next? I found my critical points. What do I do next? EVT is one of the nicest things to do. It makes the problem so much easier than when we had to do like sign chart analysis. So for those of you who are like, I hate sign chart analysis, you should be like, wow, I'm loving this. Because all we have to do is do what now? Plug in 2.
Oh, just put 5. So 2 times 5.
No.
Or the original.
Okay, the function f of x, good, but that's not also, what do we have to do? What is the entirety of what we have to do? You're missing something there. The biggest mistake that usually comes is that people plug back into the derivative and then they get 0. Now, getting 0 is not, the function could be 0 at that value. So if you get 0, doesn't mean your answer is wrong, but typically when you get 0, it should send off a signal saying, wait a minute, did I do something wrong? Because if you get 0 when you plug back in, that's most likely means you plug back into what you set equal to 0. That's why you get 0. What do I do next? So Norda was correct in giving me one of the parts, but she did not give me the entirety of what I have to do next. So what do I have to do next? You can call it by its name. If you can recall that name, you can tell me what to do. What did I do next? Well, step 2. You found the critical points. What do you do next? It literally says step 2, people. So what do I do to see if it's a max or a min? What do I do? I'm missing a letter here.
It says plug in the endpoints values.
There you go. Plug in the endpoints and critical points. All right, so let's plug in. You can't just say the points. You got to tell me what specific points there were, like what you said. You plug in the endpoints. So we need to find f of 0, f of 5, and f of 6. That's it. You plug in the critical point. You plug in x equals 5 along with the endpoints. That's it. F of 0 is easy. That's 25. The other ones, I gotta do mental math, I think. When I plug in 5, I get 25 minus 50. Oh, I get 0. Eh. Yeah. And f of 6, that's 36 plus 25, which is 61, minus 60. I get 1. All right. What's my absolute min? What's my min? Well, I'm going to point because we're running out of time. So this right here, there's my min. There's my max. I have a relative max at 0.25. I have a relative. Oh, sorry, I said relative. I don't know why I'm saying relative. Max. And then I have the min at 0.5. Now, sometimes the question asks you for where. Sometimes the question only asks you for what. Sometimes it asks you for the coordinate. All right, so if you're not explicitly, so if it says what is the absolute maximum, the absolute is 25. Now, something that I didn't note is that you could have two of these values that end up matching. For example, if this also gave me 0, which would be weird, or let's say this also gave me 25, the absolute maximum would still be 25, but it would happen at 2 different x values. So it can happen at 2 different x values and for that value. That's the process. You'll get some straightforward problems in your delta math. You take the derivative set equal to 0, plug that value back into the function along with the endpoints. Your biggest value is your maximum. Your smallest value is your minimum. That's what I have for you today. Your homework is on delta math.